Hi, my name's Connor, and I'm going to be doing a lightning talk on how easy it is to code C++ STL algorithms in Haskell. So recently there was a talk at ACCU 2019 given by Ivan Kucic, who wrote the book Functional Programming in C++, which I haven't read, but I've heard really good things about. And he presented this problem that was how to count the number of repeated values that are adjacent to each other. So he said that in a functional programming language, the typical way you do this is to pair each of the elements to the one to the right of it, to take the adjacent pairs, then to check are they equal, get a 0 or 1 based on that, and then to just sum up the ones. He then goes on to show that you can do this in C++ using an algorithm called inner product, but he gives the quote that inner product is a really cool example that you should never use. I have comments on this, but I'm not going to talk about them now because I've only got 5 minutes. If you're interested to hear more about this and other algorithms, check out my talk on Thursday. But what I'm going to do is show how to solve this in Haskell using C++ STL algorithms. So the first thing to talk about is that in C++, when we want a function object or a lambda that we're going to pass to one of our STL algorithms, we can define it or use it as one of these two ways. So we have the function objects or the operator wrappers in the function header, that's plus, or we can do the same thing with a binary lambda that just returns a plus b. In Haskell, you can do this two different ways. You have a lambda on the first line, which looks somewhat similar to our lambda. And then on the second line, we have a section, which should make you all very, very jealous because this is basically the equivalent of plus, and you can do that with whatever operator you want. Another example, if you want a predicate in the form of a lambda that returns true if your element is equal to 1, you do it like this in C++. In Haskell, you do it like this. So once again, first line is a lambda, the second line is a section. Note that the first section we saw was a binary operator. The second section is a unary operator because we bound the value 1 to our section that implements the equality operator. So without further ado, or actually there's one more thing I'm going to say that Bjorn Fowler gave a talk at Meeting C++ 2018, just like 6 months ago. It's a great talk. You should all check it out. It's on higher order functions. And he mentions that he has implemented some higher order functions to reduce sort of repeating the same lambdas that you write over and over again. And he also points out, seeing as that we're at the formerly named BoostCon, that Boost recently added Boost HOF, which stands for higher order functions, that gives you some of these sort of facilities for not writing the lambdas over and over again. So now we're going to switch to Haskell Playground, which is basically a Python script that I wrapped around the GHCI interpreter for Haskell, which is basically the same thing, but it gives you a couple extra commands and color code stuff. So the first algorithm we're going to implement is countIf. It's going to take one parameter, which is a predicate basically, and we can define this using length composed with filter and f. What is beautiful about Haskell is that it has an amazing type inference engine. If you like auto, you'll love Haskell. Basically, you go :t, and then you give it the name of your function, and it basically shows you this is your type declaration. That's what we call it in C++. It's called a type signature in Haskell. We have a predicate that takes an a and returns a bool, and a list of a and returns an int. The second function that we're going to implement is a JSON difference. We're going to use less characters because I don't have that much time. And we're going to make use of a function called mapAdjacent. If I mess up a single character, my program will crash. So hopefully that's correct. Once again, we're going to take a look at the type signature of a JSON difference. And what this is basically going to do is it's going to take the two elements that are side by side, our adjacent pairs, and then it's going to apply a binary function to that pair of elements. So in this case, because we want a JSON difference, we're going to use the minus in our section. And so the last thing that we have to do, how much time do I got left? 1:30, that's perfect. We're going to compose these two together with a section that is equal 0, and the dot in Haskell is our composition operator. If you're familiar with F#, it's the angle. We're not going to get into it too much. And then we compose this, and so play is this really cool command that I've coded that basically is going to give you the type signature of the composition of the functions. So in this case, our countIf == 0 dot adjacent difference. We could call this or name this, count adjacent equals, and it takes a list of a and returns you an integer. And then it gives you the type signature of each of the functions that make up that function composition. And then it enables you to give an input here, which we're going to use as x. And not only does it give you the result, but it actually shows you the transformation step by step. So we start with our list of integers, and generically that's a list of b. Then it applies adjacent difference, which is going to give us the difference of each of the adjacent pairs of elements, which is 0, 1, 0, -2, 0, -1. And that type signature is just from a list of b to a list of b. And then it applies countIf with the predicate == 0, which is basically going to return the number of times we see 0, which is 3 times. And obviously, when you take the difference of two elements, if they're equal to each other, the difference we get is 0. And that's all I have to say. So thank you. And C++ with Haskell equals heart.